Oh, hello. Welcome to your Saturday e-learning video. Yay! Let's go ahead and try a problem together. This is a hypothesis testing problem. I will give you guys a problem from Chapter 20 dealing with hypothesis testing, and a Chapter 19 question as well that has confidence intervals involved with it. I think those two things are both kind of I don't know, gray areas for you guys. All right, so let's check out this one together. I am not going to present also a confidence interval problem. With the Chapter 19 problem that I give you guys, just come with questions next time I see you, and we'll look at that together. Like a lot of, assuming you've got questions on it. Okay, so let's get back to this problem right here. Like a lot of other Americans, John Wayne died of cancer, but is there more to this story? In 1955, Wayne was in Utah shooting the film The Conqueror. Across the state line in Nevada, the United States military was testing A-bombs. Radioactive fallout from those tests drifted across the film location. A total of 45 of the 220 people working on the film eventually died of cancer. Cancer experts estimate that one would expect only about 30 cancer deaths in a group this size. Okay, so we've got a relatively high number of deaths due to cancer from the filming of this movie. Let's see if it's so unusually high that it doesn't seem reasonable to have been natural. So, is the death rate observed in the movie unusually high? Question A. Let's start with this one right here. All right, so this is totally a problem that we can answer via a hypothesis test. The null hypothesis here. Let's go ahead and I'm winging this, but I think it's good to wing problems just because you guys get to see any slip-ups, why those slip-ups would occur, how to amend them, all that sort of thing. So our hypotheses are these two things. The first, obviously the null hypothesis, H sub 0, is that the p-value here, the true proportion of deaths due to cancer for this group, for this film crew, is truly 30 out of 220, or let me see if I can find that value really quick. Oh, crap. Let me get a calculator. Okay, 30 out of 220 is 0.14. Okay, that's the null hypothesis. That that cancer rate, that death rate due to cancer rather, is the same even for this group here. Alternative hypothesis would be that it's higher than that. After all, we have 45 in this sample of 220 people, so that the p-value does not hold true for the film crew, and that it's higher than 0.14. Okay, there are our hypotheses. Let's go ahead and look at the model. Kind of strange here that we call it model when we've only got the one proportion z-test to work with, and we bundle in this the conditions. Conditions for this are the same as for the distribution of sample proportions, and that starts with randomization. This is definitely not met. These 220 people are all working on the same film together. We're going to go ahead and let me think real quick as to how best to describe this random sample. Even though they're not random, even though was it 54? No, that's a different problem. 220 people are not randomly chosen from the population. We need to assume that their cancer rates are representative of the larger population. We need to assume their cancer rates are representative of the larger population at hand. Of the larger pop. Okay, modern. We've got randomization worked with. Yeah, I mean, that's really fuzzy, I realize that. But again, if the randomization condition is not met, we have no tool with which to make a conclusion. So there's the randomization condition, 10% condition, clearly met. 220 people is certainly less than 10% of all people, or all adults really in this case, whom we're referring to consideration for cancer. Right, 10% condition, success, failure. Well, remember that when you check the success failure condition, you're not using the sample proportion, you're using P. So we are going to check this with 220 times 0.14. Yes, that's greater than 10, that checks out. As along with 220 times 0.86. Yes, that's greater than 10, that checks out. Okay, so, one thing I forgot to mention, and Matt brought up a good point here. Why do I call it the model twice? Well, let's not do that. Let's be verbose. Our model is the one prop proportion z-test. So we've got the hypotheses, the model worked with. Okay, on to the mechanics. Yes, we're going to use a bell curve to try to answer this problem. So let's go ahead and draw the curve. Looks something like that. At the center, this, by the way, is a distribution of sample proportions. After all, okay, let me pause there. Let me explain the logic here. I don't think that this has clicked for a lot of you guys. This bell curve assumes at the very center that the true cancer rate or death rate due to cancer is what the defendant is claiming to be here. The true proportion is claiming to be 0.14. So lying at that center is the 0.14, which is sort of the natural assumption to make. With this bell curve, we are going to compare against that 0.14 the sample. If it's really high, not too high, really low, not too low, and if this sample is really extreme, then that means it's really unlikely that this p-value we're assuming of 0.14 could explain for this sample of 220 people that made this film such a high or such a low cancer rate, whatever it happens to be. If our sample behaves more like what we're seeing here in the middle, then it seems likely that the population proportion of 0.14 could have explained the sample proportion we saw, because it's bottom line, it lies close to the population proportion of 0.14. If it's aberrant, if it's deviant, then it seems unlikely that the 0.14 could explain how the sample's behaving. That's the logic here. All right, let me see if I can somehow erase all this red crap. Boom, 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 boom. Awesome. Okay, so it's still a distribution of sample proportions. It's explaining how p-hats behave, how sample proportions behave. The expected value of p-hat is equal to just p. That's our baseline assumption, which is 0.14. The standard deviation of a sample proportion, because we have p to work with, we're using standard deviation rather than standard error, is the square root of p, q. In the first video I showed you p naught, q naught. Not a big deal if you leave those out. Over n, similarly you could put p naught here. That's the null hypothesis proportion assumption, which is the square root of 0.14 times 0.86 all over 220, I think was the sample size, which comes out to be a standard deviation of 0.0231. All right. So what's the sample actually doing? We saw a p hat for the 220 filmmakers here of 45 over 220, which comes out to be, or was it 46? Did I write that down wrong? Oh, I did. That's a typo. This should be 46. So even more than I originally had. 46 out of 220. Sorry about that mistake. Comes out to be 0.209. So we're sitting over here at 0.209 with a standard deviation that was low of 0.0231. So we are quite a few standard deviations out, actually. Well, again, we want to find the p-value. That's everything that we're shading in red, because remember, the alternative hypothesis here was that the true proportion of cancer rates among this 220 people is not the 0.14 you would see in the population at large, and that it is different, perhaps due to the exposure to radiation that they suffered during the filming of The Conqueror. So it's because, again, just following the alternative hypothesis, if we're checking to see if p could be greater than 0.14, we want to see where our sample is right here, and then check the area under the curve greater than that. So the p-value is equal to the probability that a sample proportion could be greater than or equal to 0.209, which we can't answer directly, but because we know the z-score, wait a second. Yeah, we still need the z-score, sorry, which is equivalent to the probability that, well, let's find the z-score for this thing, 0.209 minus 0.14 over that standard deviation of 0.0231 comes out to be 3.14. Okay, so we're working with the z-score for this sample proportion, 3.14 here, which this p-value is 0.0008. So 0.08 All right, so that's an awfully low p-value. This is a great time to conclude. We'll go back to blue here. Conclude piece. Why can I not spell? Due to low p-val, we'll just put in parentheses 0.0008. We reject the null hypothesis assumption that there is a true 14% death rate due to cancer among this group of people in favor of H sub A. That P, the true proportion of deaths due to cancer among this film crew, is greater than 0.14. Okay, so there's A. B's really fast, thankfully. All of this was A. B is asking, does this prove that exposure to radiation may increase the risk of cancer? Two definite no's as to why this does not prove that exposure to radiation may increase the risk of cancer. First thing, no. Even though our p-value is low, right here, we did not find a p-value of 0. We didn't say that there is a 0% probability that when you get 220 people together, that such a high death rate due to cancer could not be explained by a naturally occurring death rate that we see all across the nation of 14%. Yes, this sample has a high death rate due to cancer, but we don't prove beyond a shadow of a doubt with this p-value that it could have occurred naturally. 8 times out of every, what would that be, 10, 100,000, 8 out of every 10,000 times you would see such a sample behave this way. So which means, again, it's not impossible, it's just improbable. No, p-value still leaves room, spelled with an R, not an F, room for this to occur naturally. Okay, that's the first thing. Second thing is no, for different reasons. Lurking variables. Who knows? Again, notice when we were filling out the conditions, we really fudged with randomization. There might be lurking variables. Lurking variables, things we can't account for that were similar among this group of 220 people, but that we don't know about. Lurking variables could account for this high cancer rate. All right, there's your video. I'm going to post a couple of problems in your bundle. We're going to get this video submitted to YouTube for now. Have a lovely Saturday, guys, and I will see you later.